Hello, good morning, students. Can you hear me and see my screen?
Yes, Prof.
Thank you. Yeah, so let's start directly. Yeah, it's already 10 a.m. Hold on, let me just check. I think I'm recording already. Yeah, so first of all, I want to just finish up tutorial 7, the last question, right? Because the last question is also your past year finals question 3 here. Okay, so by the way, the past year finals, the answers are already uploaded in X already. Okay, so these are all the answers, right? So as I mentioned, you should ignore question 1B as well as question 5, okay, because we didn't cover that. So therefore, you just ignore the two questions there, okay? But maybe question 5 you can go through after watching the recording on surface integrals, right? So as I mentioned, I'll be doing a recording on surface integrals such that you can review on your own time, at your own time after the exam, right? So as to get ready for your electromagnetics E&M lah, right? Electricity and magnetism module next trimester, right? So let's quickly go through the question 3 here. So it says here that you have a heat shield that is made from a composite material that has a solid region E described by the sets here, okay, the inequalities here. So you can see that the region E, right, is just defined by two inequalities. One of them is Z must be bounded from the lower bound, which is this root of x squared plus y squared. But now, by now, you probably know that this root of x squared plus y squared is really just root of r squared, right? So root of r squared is really just r, right? Root of r squared is really just r. So in cylindrical coordinates, this will be the probably most advantageous, right? Such that you can perform the integration more or less easily, right? More easily. So therefore, it will be from z equals to r to z equals to 1. Okay, so it looks like a cone, right? Which is something that we have seen before. And then it is also bounded by this second inequality, right? Whereby the cone is supposed to be of radius 1. Okay, that means your cone, right? Maximum at the so-called broadest part of the base of the cone is of a radius 1. Okay, so because this is actually just r square equals or less than 1, right? So that means it's a unit disk. Okay, so if you sketch the projections of the heat shield here onto the three coordinate planes, and you're going to get this. Okay, so you can see quite simply, this is a unit disk, right, which is given by the second inequality. And then for your projections onto the zx as well as the zy plane, they look exactly the same, right? Because the zr plane projection looks like that. Okay, so since r is in all directions, x and y, so therefore, obviously, zx and zy plane will clearly show you the same so-called projection. Okay, it's more of like a sectional view lah. Sectional view or projection doesn't matter, right? So therefore, you can see that indeed, as we mentioned, right, it is bounded from the bottom here. Okay, so your bottom is actually your z equals to r. Okay, so this is z equals to r, and then the top will be z equals to 1. Okay, so clearly it is bounded in this cone here. So that will be 6 bucks, right? You draw everything correctly, and then you label the curves, and then you also label the intercepts, right? Your axis intercepts, namely your z intercept, x intercept, as well as your y intercept. Okay, so label all those intercepts clearly, and you'll be getting the full marks. So that will be for 1A, I mean for 3A, okay, in this question here. So then let's look at part B. So part B is to set up an integral in Cartesian coordinates that gives the volume of the heat shield, but it says do not evaluate. So 4 marks, I just write down the integral will do. Okay, just write down, no need to integrate. So for part B, you can see here, okay, so part B, because they ask you in Cartesian, so you have to follow. So in Cartesian, the dv here is given by the standard dx, dy, dz, right? In any order, doesn't matter. Okay, so therefore, maybe one of the easiest way to integrate is to integrate with respect to z first. I mean, there are other ways to integrate, no issues with that. Okay, if you write down a different integral, but with a different order, but it still gives you the same volume at the end, it's totally fine as well. Okay, so that means that the answer here may not be unique lah. Okay, it is not unique, but you must use Cartesian following the question. So now you can see that if you follow this order, that means dz first, right? That means we are actually looking at an element that is from z equals to r to z equals to 1. So this will be your vertical element that you want to use. Okay. Then after that, you take the vertical tower, right? The tower element, right? The volume element. Then you just sum over the region R, which is given by the unit circle here, or the unit disk. Okay. So that's the idea lah. So therefore, you must sum from what? You must sum from z equals to r ma. So z equals to r in Cartesian, right, is your root of x squared plus y squared. Okay. So you can see this is the lower bound. Use a different color here. You can see our lower bound must be z equals to r. Can okay? But you cannot write z equals to r because z equals to r. R is what? A cylindrical coordinate system, right? Or polar coordinate system. Okay, but this one in Cartesian, so just put in the whole expression for r in terms of x and y. Okay, I think that will be quite obvious. So then z equals to 1 will be the upper bound. Lor. Okay, so this will be z equals to 1, which is the upper bound. Can okay? Yeah. So once you have that, right, then you can see that you have to integrate over x and y. Okay, so integrate over x and y, right? You just look at the unit this here. Okay, because after you integrate respect to z, you don't need to look at the z axis already. Okay, that means you don't need to refer to the projections on the zx plane and the zy plane, right? You refer to the xy plane because now you're integrating respect to x and y now. Okay, so with respect to x and y, maybe you can do dy first, right? If you do dy first, that means the element becomes like that. So this will be your element. Okay, so if you do dy now, right? Then you look at what's the lower bound for y. Lower bound for y must be this guy, ma. Okay, but I think now you know lah. This will be y equals to minus root of, because it's a unit this, so it must be root of 1 minus x squared. Lor. Okay, so this is the lower bound, right? So then the upper bound will be y equals to root 1 minus x squared. Okay, so you can see that the bounds for y here, right, is embedded into the, wait, let me see, use different color. So you can see that you have your y equals to 1 minus x squared. Okay, so this will be your lower bound for y, right? And then the upper bound for y, right, is root of 1 minus x squared, positive root of 1 minus x squared. Okay, so in fact, you are looking at the xy plane here, right? The unit disk on the xy plane. Can okay? Then obviously the final bound for x are minus 1 to 1 right? So the final bound for x should be pretty clear okay? Because you want to sum from the first element here, right, to the last element here, right? That means you're summing up, all the rectangles, all the slices right? So therefore you sum from in x direction, right? From minus 1 to 1. Okay? Oops, I just realized that I kind of wrongly labeled this. So this should be y and this should be x. Okay? Doesn't matter lah. If you swap, right, it's actually the same meaning. I mean, if you swap, it is still the unit disk. Okay? But just that the element here you have to draw horizontal. Okay? But never mind. Let me just like swap this back, okay, to the standard y being vertical and x being horizontal. Okay? So yeah, that's it. So this is 4 marks, right? Just by referring to your projections. Okay? So this will be the volume in Cartesian, but no need to evaluate, so just write down will do. So finally, let's look at part C. It says
Prof,
here that if the density of the composite material is described by the function given by this 1 over 1 plus rz holding square, you're supposed to set up and evaluate an integral in cylindrical coordinates that gives the mass of the heat shield. All right, so we know that mass, right, is integral of density over the entire volume. Okay, but in this case, you have to give it in cylindrical, right? So as I mentioned earlier on, cylindrical is probably the best coordinate system to use because you have z equals to r as the lower bound, and you can see that the region of integration in the two-dimensional plane, right, is also part of this. Okay, it's also a this. So therefore, it'll be easier to integrate. Right, so as mentioned, you can see that in cylindrical coordinates now, right, cylindrical coordinates, right, your dv must be r dr d theta dz. Okay, so you can see, right, dz r d theta, oh sorry, dz r dr d theta. Okay, the order doesn't matter, right, because multiplication is commutative, right, order doesn't matter. Okay, so you just put it in an order, right, that you feel is easier to integrate. Okay, so therefore you can see that the density function, rho, right, so I integrate all the so-called small masses, right, the small masses, each small mass is rho dv. Okay, dv is like a small element, right? Then you treat the density as a constant over the entire small element. Okay, so actually this rho dv is your what? Is your dm, right? It's a small mass, right? Then triple integral, sum out all the small masses over the entire volume. Okay, then you get total mass, right? So integration is just summing. So therefore, you can see that plug the density function into the expression. Okay, and just be careful when you have a r here. Okay, so this r here, right? So certainly, of course, you can put the r, what do you call that, in the fraction instead. Okay, so therefore, after you integrate the, let me see, correct. So after you integrate this integrand, right? Wait, dz r dr d theta. Hold on, am I missing? Correct. Okay, so you can see that, right? Now I have to integrate with respect to dz first. Okay, so I integrate this expression with respect to dz. Okay, so apparently I forgot to remove the dz here. Hold on. So there's an error here. So this dz integrated already. Okay, so no more this dz. I forgot to remove that. Okay, you can see the integral respect to z disappear already, Can, right? Okay. So you can see that this is a function, right? This is a reciprocal function or a fraction in z, what? Right now, a fraction in z. So what I need to do, right, is because now I need to integrate. Okay, so this is power minus 2, Understand, right? So therefore, if I integrate, the minus 2 become minus 1, right? Minus 2 become minus 1. Then I get 1 over minus 1, which is just minus 1, So therefore, I get minus 1 here. You see, okay, then you can see the power become minus 1, right? So the power disappear. I mean, the power square here, right, disappear after I integrate. Okay, then obviously I must use a reverse chain rule. So you can see that there's a RZ here, So reverse chain rule is going to give me 1 over R. Okay, if you cannot see it, then it's okay. You can just use your U substitution, right? For example, if you let your U equals to 1 plus RZ, then du equals to r dz, Is that right? Okay, then this dz will be giving you 1 over r du. Okay, so this one you can use substitution, you can just use reverse chain rule directly. Okay, yeah, so after you have integrated respect to dz, you're going to get this minus 1 over r times 1 plus rz, then your limits will be r to 1 here. But then because you have this r here, So therefore, the r there, right, will cancel off. So this r here will divide away the r here. Okay? Yeah, so therefore, after you sub in the limits 1 and r, then you get this third row. Okay? Then after you just integrate with respect to r, you can get the first one, the first term giving you tangent inverse r. Then the second term, right, just giving you ln 1 plus r. Okay, then you sub in limits, then you times the 2 pi. You can see that actually this integration with respect to theta, right? From here, this expression, right, is what? Separable. Okay, this expression, you can see that this expression, wait, let me see. Yeah, you can see that this expression has no theta, right? It's just a function of r. Then after you sub in z, right, eventually it's just a function of r. Okay, sub in the z limits lah. Then after that, right, so therefore, the limits are also constants. So separable and limits constants. So therefore, you can split up into two independent integrals. Okay, faster if you don't split it up also can, you just do one by one. Right? So therefore, you sub in the limits, you get 0.58. Okay, roughly 0.58. So that's the mass of the heat shield. Any questions on this past year integration, triple integration problem?
Sir, yeah,
Yeah.
so the one where you underlined in purple color, right, for the 1 over 1 plus RZ square, right? Then
Yeah.
one you said to use substitution to reach the next part, right?
You can either just visualize it using the reverse chain rule, or you can also use U substitution.
Okay.
So if you use U substitution, you just like let you just like let U equals to 1 plus RZ, let's say. Okay, if you let U equals to 1 plus RZ, then obviously du equals to R dz. So therefore the dz, right, must be 1 over R du ma. Correct or not? So therefore this integral, the innermost integral become integrate. Okay, forgot the limits first. Let's forget about the limits first. So now you get 1 over U square ma. 1 over U square. Correct lah, 1 over U square. Then what's the dz? 1 over R du ma. 1 over R du. Is that right? So if you integrate this, then obviously you're going to get 1 over R. Then this 1 over U square, you integrate, you just get minus 1 over U. Is that correct?
Yes.
Then this is this one.
Yeah, I see.
Can
Yeah.
After you sub back the U lah. After you sub back the U, then you can just get this one.
Okay.
Hmm.
Thanks. Thanks.
Any other questions?
Prof, then what will happen to actually the negative one on top? Because, like, is it due to the application of the substitution rule there?
Oh, you mean this minus 1
Yeah, because like the next step is 1 over 1 plus r square minus 1 over 1 plus r dr.
Okay, wait, where's my minus 1 here? Let me see. So I can solve this r if I integrate, if I sub in the limits, right, I should get minus 1 over 1 plus r squared. Yeah, right, Okay, maybe I have made a mistake here in the sense that it could be 1 over 1 plus r minus 1 over 1 plus r squared instead, because of this minus, right?
Okay.
Yeah, I could have made a mistake here. Okay, that means I should probably I might need to like swap the terms, but let me check first. Okay, so let me check first before I correct myself if required. Then I'll just make a correction. Okay, yeah, it seems that this minus 1 here is not accounted for in this third row. So I'll check this part. Any other questions? Okay, good. So yeah, so that'll be it for this tutorial 7, the last question. So then we move on to our tutorial 8. Okay, so tutorial is on vector fields and line integrals. So question 1 is just testing you on the understanding of a vector field and also the computation of Jacobian and divergence. Yeah, so this one actually how you match the vector field given to the plots of the vector fields below, right? It's just actually maybe you just like sub in some point, right? Then you see like which of the plots here conform to the points that you have drawn for the vectors. Okay, so actually like quite easy to see that this xy, right? So f equals to xy. Okay, so what this means, right? F equals to xy here, right? So that means if that means the x component is x right now, x component is x. So therefore, right, if you look at this vector field f, you just like make a small sketch lah. Okay, so let's say in the first quadrant, you'll be able to see it already. So you can see that when x is positive, so let's say this is your x, then the component is x, right? So x is positive. So therefore, maybe at this point, the x component must be positive also because x itself in the first quadrant is positive. Okay, so this is your x component. You see, then your y component, is y. So therefore, at this y, the y component is also positive because it's in the first quadrant. So that means y component for the vector field must be positive also, so pointing up lah. Okay, so that's all this xy is going to give you a radial vector field. Right, it's going to give you a radial vector field. That means at this point, right, this got to be your f. Okay, so this is your f of xy. You see? Okay, so therefore from here you can You just draw 1 point can already. And you look at the three plots and you compare lah. So which one is the vector at the first quadrant pointing outwards one? Pointing in the radial direction. The only one is B ma. Correct or not? You can see that this one is like point the wrong direction. This also doesn't point in the correct direction. So therefore this one the radial direction must be B. Okay? So therefore this B is f of xy. Can right? Okay? Then you just do the same for the other two lor. Just do the same for the other two, and you're going to see that, right? Okay, so you can look at this G. So G, what does that mean? G means this is x component is minus y. So you just draw the first quadrant. Okay? And this is minus y, correct or not? So that means if the y is here, then this y is positive, correct or not? But this is x component being minus y ma. So that means at this point, it must be pointing in this direction. You see? X component is minus y, like y is positive. So obviously x component must be pointing in the negative x direction, what? Correct or not? This is minus. Can Then the y component is x. So if the y component is x, then this is x. Then your x is positive. So therefore the y component must be positive. You see? Okay? So therefore where's the vector going? The vector must be going this direction. Correct? Okay? So therefore this is your G. Then you look at so this one is f already, it cannot be this one. So it must be this one also. A must be what? G of xy. Is that alright? Because you can see the vectors here is pointing, in the same direction as your plot here. Okay? Can Then this h, you just do the same thing. So you just draw a first quadrant. Then you can see that this is x. So when x is positive, then this x is also positive, so pointing towards the right. But then this y is minus y. So when your y is positive, the y component will be negative. So therefore, it must be pointing down. You see? Okay, so where's the fellow going? The fellow is going, okay, wait, let me adjust the arrow magnitude a little bit. Okay, so the arrow must be pointing in this direction. You see? So this must be your h. So you can see that it follows this one. Okay, so this must be h of xy. Any questions?
Prof, can you explain GX again?
G.
Yeah.
So G, right, you can see okay, you can see that this minus y, right, it is minus of the coordinate value y leh. So when y is positive, because the first quadrant, this y must be positive, like 2 lah, for example. Then you sub in y equals to 2, you get minus 2, correct not? So the x component of the vector must be minus 2. So minus must be pointing in the left direction, towards the left. Is that all right? I think this is the part probably is the confusing one.
Prof, then in this case, can you use the fourth quadrant? Like you put y as negative and x as positive.
Oh, yes. Any quadrant is okay. Any quadrant. So if you use the first quadrant, right, that means the y is negative. So if the y is negative, that means it must be pointing positive, in the positive direction. So you can see this. So at this y, because the y is negative, so that means at this point, right, this y is negative, minus must be positive. So it must be pointing in this direction. But the x is also negative. The x is still positive. Okay, this x is still positive. So therefore, it is pointing in the upwards direction. That means the vector, right, at the fourth quadrant must be pointing like that. There, which is here, what? Right now.
Okay.
So this one must be G. This arrow is like maybe somewhere here. Then this arrow is like somewhere here.
Okay.
Is that right?
Can.
Okay, so this has to be G.
Thank you.
Yeah, so do I need to do the Jacobian and divergence or not? Evaluation of the Jacobian and divergence. This one just differentiate, and then for the divergence, you just differentiate sum together.
Can do one.
Okay. Yeah, so maybe I do for G lah, right? So the vector field is already given. So therefore the Jacobian of the vector field G, okay, is equivalent to, generally it'll be a function of xy lah. Okay, maybe I put. So generally it'll be a function of xy. But in this case, probably not. So you can see that the Jacobian here, right, it must be a matrix ma. So this one, you have to differentiate respect to x. So the first column, you do del x. So therefore del x, first column, minus y, differentiate respect to x, of course, get 0 lah. Okay, then x differentiate respect to x, just get 1, right? Then after that, the second column will be del y. So del y is -1 and 0 respectively. So that's it. That will be the Jacobian for your vector field G. Okay. Then what about the divergence? So the divergence will be the gradient operator operate or dot product with G. So therefore it says that you differentiate the components, right, with respect to their own directions. So this one will be del x, del y dot minus yx. Okay, so certainly you're going to get 0 lah. So this one, you just get 0 plus 0. Because you differentiate minus y with respect to x, you get 0. Plus, then you differentiate x with respect to y, you get 0. So the divergence is actually 0. Okay, you can see, you can argue logically why is it that the divergence is 0, right? Look at this field. This field is like rotating, just swirling like that. Correct or not? It's not like expanding or contracting. So there's no expansionary effect, there's no outflow effect, there's also no inflow effect. Okay, it's a pure spiraling flow field or vector field. Okay, so certainly, right, the divergence will be 0. Okay, because the divergence represents what? Expansionary effect, or you can say it's the degree of outflowness of the field. Can okay, so certainly for vector field G, right, divergence will be 0. For vector field F, the divergence, right, will certainly be positive. Okay, because it's like expansion, right? So this one we deal with is we look at such a field in the lecture before. Okay. Then for H, H I'm not sure. This one you have to calculate. Okay. Then of course the divergence will tell you. So yep. So that will be for question 1. Then question 2. So this one is just a 3-dimensional vector field. Supposed to compute the divergence, Jacobian, and the curl, and then determine them at the point 1, 2, 3. So this one, do I need to do? Just differentiate and then take divergence and then compute curl. Then you just sub in the coordinate x equals to 1, y equals to 2, z equals to 3. Then you just get the values here. No need, right? This one, mechanical. So this one, I think you DIY. Yeah, so then question 3. Okay, question 3 I want to go through. Because I give you the vector field here, and I ask you to use this vector field graphing tool from GeoGebra. Okay, I haven't gone through this in lecture yet. So just make use of this question to go through with you as well. Okay, so when you want to visualize the vector field, right, you can actually use this online graph. Okay, you're supposed to evaluate the curl vector and then explain why the curl is 0, is the 0 vector, despite the vector field appearing rotational. So let's look at the vector field first. Okay, so of course, obviously you can see that, right? The vector field here only has the x component and the y component. So there's no z component, right? So that means your vectors are purely in the horizontal plane. Okay, on the xy plane, if you like, right? On the xy plane. So the z is 0. So no z component. Okay, no vector that is sticking out. So therefore, if you were to plot them in the graph plotter here, okay, I already plotted them already, you can see, right? Minus y over x squared plus y squared, and then x over x squared plus y squared, okay, for the x and y components respectively. And then of course you can mess around with the arrows and whatnot, okay. Then you see this is the field. You can see that the field is like rotating, right? If you put in an object, right, it's going to flow around. Okay, let me just hold on. Maybe I go to the next page. So this is your question 3. So you can see that this is rotational vector field, right? And then if you put in like some object like that, right? Then this object is going to follow the flow field, correct or not? So it's going to just flow around. You see, okay? So it is like appearing to be rotational, right? But then if you compute the curl vector, right? If you compute the curl vector, which is not difficult to compute, because you just have the gradient operator cross product, right, with your vector field. Okay, so your vector field is F. So you can see your curl operator, del sub x, del sub y, del sub z, cross with minus y over x squared plus y squared, then x over x squared plus y squared, and then 0. Okay, so because you don't have any z component, so that means your vectors are only in the plane. Then this shows that, right, the curl is going to be having an axis, right, that is in the positive or negative z-axis. Okay, that means it must be along the z direction, right? So what I'm trying to tell you, right, is that when you see that there's this zero component here, right, you can straight away put 0 and 0 here already. Okay, because your curl, your rotational axis direction must obviously be pointing out of the plane, because your vectors are already in the plane, what? Okay, can right? So it's pretty obvious that I can see that if you cover this first row, right, you take this del y on 0. Del y of 0 is 0. Then del z of your vector field only containing x and y terms, right? So therefore, it is also going to give you 0 when you differentiate respect to z. Okay, so therefore it's clear that this will be 2 zeros. Okay, but then if you cover the last row, right, because you want to get the last component, and you take the derivative, okay, take the cross product, right, of the two rows, of the top two rows, right, then you are also going to get 0. Okay, so this one I leave you to check. So therefore you are getting the 0 vector, right? You get the 0 vector. So therefore, if you get the 0 vector, that means no curl. But then the field is appearing rotational. So what's going on here? Okay, so this is actually, this question is actually to make it clear to you that curl means that the effect is to rotate the object when it is at a particular point. Okay, that means it is actually a point property, right? But then when the field appears rotational, as you see here, right, it doesn't mean that it is going to spin or rotate the object. It is just going to make the object flow in a circle. Okay, so therefore this is the difference, right? So let's say if I have an object, okay, I have an object that looks like that, right? I put it inside this flow field, but because the curl is 0, so the object actually don't feel any spinning effect. There's no so-called rotational or spinning effect on the object. So the object will just move around in a circle because it must follow the flow field arrows, but the orientation doesn't change. You can see the orientation is always the same. Okay, so the object is going to like flow following the flow field direction. Can you see? Okay, so object in flow field or in the vector field flows around in a circular path, but does not rotate or spin, okay, about its own axis. Maybe you're right. Does not rotate about its own axis because the curl is 0. Is that right? Okay, so the curl being 0 is a matter of the spinning effect, right, on an object inside the flow field. Okay, it is not how the flow field looks. The flow field can like flow in any curvy path, right? But it doesn't mean that you have you possibly have a curl. Okay, so you have to calculate, right? So therefore you have to calculate the curl. Then you look at the so-called vector that you get, right? Then you can argue, like for example, is the object going to undergo some kind of spinning effect, right? And what direction it is spinning. Okay, about what kind of axis, right? About what axis it is spinning. Okay, so this is more of a concept question. Okay, just to clarify the concept between the field that looks rotational and the curl itself. Yeah, so this is for question 3. So this one I've gone through. Question 4, do I need to do or not? Because question 4 like very similar to the lecture examples. Basically just make sure that the field is conservative by having 0 curl. And then if the curl is 0, that means it's conservative. Then you have to just do the integration thing. Do I need to do any of them? So you can see that 4C, the curl is not 0. Okay, 4C, the curl is not 0. So if the curl is not 0, not the 0 vector, then it is not conservative. So not conservative means the components here, right, the 3 components here is not obtained from differentiating some scalar function. Okay, that means it is not a gradient vector. this part C, this vector F here, is not a gradient vector. Okay? Because it says no here, right? So if you try to do this one, you'll realize that the curl of F is not equals to the zero vector. It means you get some curl. Okay? And the moment it is not equals to the zero vector, then it implies that F is not a gradient vector of some scalar potential function. Okay? It's not a gradient vector. Right? So it's not possible for you to find the scalar potential function. You can try to integrate, right? But when you integrate different components, you're going to get different functions, right? Okay? You cannot possibly satisfy the consistency in terms of in terms of integrating different components. Okay? Whereas if you have A and B, as demonstrated in the lecture, right? I can integrate f sub x, I can integrate f sub y. Okay? But I always end up with the same scalar potential function. Right? So that's because this is a gradient vector. Then you can do that. Okay? So I suppose I don't need to go through 4A or 4B. No need? Okay, so good. So on DIY. Yeah, then let's look at 5. Okay, 5 is a force field in newtons defined. So then you're supposed to show that the force field is conservative. So basically just find the curl lah. Okay, so you can see that this one got no z component, so just throw a 0 to it lah. Okay, just throw a 0 to the z component. Then after that, evaluate the scalar potential. Then once you get the scalar potential function E, right? Then you want to calculate the work done in part C. So therefore, you just use the scalar potential E, right? And take E of 1, 1 minus E of 0, 1. Okay, so there's no need to make use of this curve, right? Because since it is conservative, the work done just depends on the start point and the end point, right? Along any curve, the work done is also the same because the field is conservative. This one, do I need to do?
Can you do part A?
Oh, part A.
Yeah.
Sure. Okay, so okay, let me just take a screenshot. So to show that the field is conservative, right, as I mentioned, you just take the curl, and therefore this will be del sub x, del sub y, del sub z. So it says sub means like you're differentiating respect to that subscript variable. And then this guy, you just have x over y squared plus x. The second term is minus, okay, so this is minus of this whole thing. So it's minus of x squared plus 1 over y cubed. And then the third component will be 0. Okay, so you just put a 0 for the z component since this is entirely in the plane. Okay, so once you have that, right, you can straight away put the 2 zeros at the x and y component for the curl. Okay, so then the last component, you just have del sub x. That means del x on this term. When you do del x on this term, the 1 and the y cube, they are constants. So therefore, you are going to get just 2x or minus 2x over y cubed. So minus 2x over y cubed. Is that right? Because plus 1 over y cubed is a constant, what? So you differentiate respect to x, the value becomes 0. Okay? So you get minus 2x over y cubed. Can. Then you have to minus del y on this. So when you do del y on this, right, you can see that there's an x over y square here, right? So differentiate this guy respect to y. Okay? So obviously the y is going to become y cubed, right? Because it's y to the power of minus 3, right? So then therefore you bring down the minus 3. So therefore you have, let me see. Oh, sorry, you bring down the minus 2. So you get minus 2 times x, because x is a constant, then divide by y cubed, okay? Because you bring down the minus 2, then the power become minus 3, right? So therefore you get over y cubed here. Can. Then the x is a constant, just put it down. Then the minus 2 comes from the power being brought down. Is that right? So therefore you can see that this is giving you the 0 vector. So this guy will be the 0 vector. Okay, because it is minus 2x over y cubed plus 2x over y cubed. Is that okay?
Okay, thank
So once
you.
you get the zero vector, then the field is conservative.
Wait, Prof, can you explain why the top two are zeros?
Oh, why is it that I can straight away put zeros? Okay, so if you don't know that, right, you can also just compute you can also try to differentiate. Then you will get zero as well. Okay, but the logic is this. The logic is, right, you look at your field, then if you try to draw your field, what happens is that, right, you only can draw the field on the xy plane. Because the z, right, that means the field itself is on the xy plane. So therefore, okay, let me see. This is x, y, z. We will try to draw this vector field f. So the vector field f, right, you can see that because you don't have any z component, that means the field itself, right, doesn't have any arrows that is sticking out, right, in the z direction. So this field, I don't know how it looks like, but that doesn't matter. So it is always having arrows that is on the xy plane. I just anyhow draw a few arrows. Okay, so all these arrows is on the xy plane and they only point in the x and y directions. Each arrow will only point in the x and y directions. Okay, there is no z component. You cannot stick out the arrow, right? Such that there is a component that is in the z direction. There's no z component, what? These are x components or y component. There's no z component, ma. So therefore, for such a vector field, right, if there is any curve, if you have a curve, let's say there's a curve, maybe looks something like that. Okay, let's say the curve here, right, is like that. If there's any curve here, then the axis of the curve, according to the right-hand rule, must be pointing in the z direction, what? You see that? This is the axis of the curve, right? So maybe, let's say at this point, right, there's a curve that look like that. Okay, then you can see that the axis, if you use your so-called right-hand rule, right, the axis of the curve must be pointing vertically downwards. You see? So therefore, the curve must be always be in the plane such that, right, its axis must be along the z direction. Understand? So therefore, you can see the curve is only in the z component. There is no x and y component one. Is that okay?
Okay, can.
Can okay. Yeah, so this is 5A. So I don't need to do the rest, the scalar potential thing and the work done thing. Okay, so this is done. And this one you DIY. Okay, then question 6 also the same kind of question. Do I need to do? Actually, no need, right? Question 6. It's just that I don't give you the functions f, g, and h lah. Okay, but then you can still kind of integrate because you can like integrate small f get big f, then integrate small g get big G, integrate small h get big H. So you can still find the scalar potential in terms of the big F, big G, and big H function. Okay, then after that, conservative already, you just use the scalar potential to get the path integral or the
Uh,
line integral.
Prof, for the scalar potential in the answer, do you have to put that the big G is an antiderivative of your G small g, or do we just omit that part?
Uh,
No,
in your working, you have like a step that says integral of small g of y. Then if you write integral of small g of y equals to big G of y, then I will know lah. That means I will know that your big G is the integral of small g. So okay lah. Then don't
alright,
need to write because it's
okay.
pretty clear stated in your working.
But if you never say that in a working, you must write it down.
But when you do your working, you confirm
Alright.
will write something like that, right?
Yeah. Alright.
Ah,
Yeah. Okay.
yeah. Of course, if you want to be safe, you can just write lah. But I think if your working is clear, then actually there's no need to state. It's pretty obvious.
Okay. Then for question 6, why is there no plus C? Or
Because the plus c can be embedded into any of the functions here. So this h of z, for example, inside can have a constant because a function can be very general, right? It can also include a constant. So the plus c could be inside this expression already. Can be inside any of the f, g, and h.
but if you write a plus C separately, will it matter?
It's perfectly fine.
Okay.
Perfectly fine.
Okay.
Okay. Any
Alright.
other questions? Okay, good. So this one I don't need to go through. So this one DIY. Okay, so now line integral. So probably I need to go through already. Okay. So you're supposed to wait. Wait. Oh, this one I think you skip. Okay, this question you skip. Because this line integral is for scalar functions. So this one skip. Okay? That means it's not tested lah, because we didn't go through. But if you want to practice, you can of course go through yourself. Okay? Because this one is for scalar line integrals. Scalar line integrals. So now we move on to the vector line integral questions. Okay, question 8. Do I need to do? Maybe this one I think I better do. This one. Okay? So just to make it clear that you need to know how to parameterize a path that is defined. Hold on, let's see. So you can see that the question actually states that you have a path that is a straight line path, right, from 1, 1 to 3, 5. So from 1, 1 to 3, 5 you have to write down the path equation first. Okay, because if you don't know the path equation, then you cannot parameterize the path. Then if you don't have the r of t of that path, then you cannot do the line integral. Okay, so therefore 1, 1 is maybe here, right? So this is 1, 1. And 3, 5 is maybe here. So this is 3, 5. So that means the path must go from 1, 1 to 3, 5. Okay, and it says that it is a straight path. So 1, 1 to 3, 5, this direction. Okay, so in this case, your path equation can be worked out from these two coordinates. Okay, so it's just y equals to mx plus c, right? Or you can make use of any of the points here. Okay, and then you have your point slope form. But what is the slope? So the slope can be found easily. So slope m, right, is equivalent to change in y, so which is just 5 minus 1, divided by change in x, which is 3 minus 1. So the slope is just 4 over 2, which is 2. Okay, so straight line, the slope is positive 2. And then you just have y minus y1, right? So y minus 1 equals to m. Okay, maybe right. Y minus y1 equals to m x minus x1. So maybe x1, y1, I'll just use the 1, 1. So y minus 1 equals to 2 times x minus 1. Okay, so that means your y as a function of x will be y equals to 2x. So there's a minus 2 plus 1. So you have a minus 1 there. Okay, okay, so 2x minus 1 will be your path equation. Okay, so now you need to parameterize, right? So let r of t, okay, wait, I use a different color. Let r of t, which is just x of t, y of t, correct not? X of t, y of t. Then you just let your x be t, for example. Okay? If x is t, then y got to be 2x minus 1. So therefore, 2t minus 1. Is that alright? Can, okay? So basically, this is your y equals to 2x minus 1. Okay? Because you have to follow along this path, what? So therefore, that's your parameterized path already. Okay? That means the path is described in terms of parameter t, Can, so once you have that, then after that, the r prime, because you calculate r prime, so therefore r prime of t. So r prime of t will be just 1, 2. Okay? Because you differentiate with respect to t, you get 1. Differentiate 2t minus 1 with respect to t, you get 2. Okay? And 1, 2 is legit, right? What's the deal with 1, 2? 1, 2 is the direction along the path, No, this is the velocity vector, So if you move from 1, 1 to 3, 5, the velocity must be always along the 1, 2 direction, what? Make sense, Okay? So it's a constant, because everywhere you also get the same velocity vector. Okay? That means you must be traveling along the path at all times. Okay? Yeah, so once you have that, then after that you just write down the f in terms of r of t. Okay? So f in terms of r of t, f in terms of r of t. So that means substituting the x by t, substituting the y by 2t minus 1. Okay? So you see this is x squared minus y minus, x squared minus y. Okay, so let me write down first. So this is x squared minus y, x minus y squared. So what's your x? Your x is t, what? So it's t squared, then minus y, but y is 2t minus 1. So 2t minus 1. Then the second one is t, because its x is t. Then minus you have y square, which is 2t minus 1 whole thing square. Is that right? Can okay. So obviously you can probably expand a little bit. So this guy will be just t square minus 2t plus 1, the first row. Then this guy will be what? T minus 4t square. T minus 4t square. Okay, wait, let me put a bracket. Or else I mess up. T minus 4t square minus 4t, right? Because it's minus 2t minus 2t. Okay, so therefore we have minus 4t and then plus 1. Can okay, so maybe just a final simplification. So this guy is going to give me minus 3. Oh, sorry, it should be minus 4t square. Then I have, this is minus, so become plus. So actually it's plus 5t minus 1. Is that okay? Can okay. So this will be my f in terms of the parameterized r of t. So what I do now is to compute the line integral. Okay, since everything is already evaluated. So integrate, okay, the line integral. So therefore, this path c, okay, from 1 to 3, 5. So hence I integrate over path c, right? F dot r prime dt. Okay, so integration over path c will mean that you are integrating from t equals to what to t equals to what. But because your t is x, what? You see, you let your x be t, ma. So that means the t must be from x equals to 1, right? So this is x equals to 1 to x equals to 3. Okay, so therefore t must be from 1 to 3. Can okay, so because these are t equals to x, right? So therefore the limits must be from 1 to 3. Okay, so it depends on what your parameterization is, right? If you let your t be y, cannot, can. Then you have to work out what is x. Okay, then in this case, if t equals to y, then t will be 1 to 5, right? Depends on your parameterization. So therefore, we stick with t equals to x. So it'll be 1 to 3. And then you just plug this thing. So multiply, or dot product, not multiply, dot product with 1, 2. Then dt. Is that all right? Any questions with this statement? This will be your line integral. Can okay. Then the rest is just evaluating the integration already. So therefore, this will be integration 1 to 3. Then you take the dot product. So it's t square minus 2t plus 1. Then dot, so this is minus 8t square. Minus 8t square plus 10t minus 1. Okay. Then this one you integrate 1 to 3. So this one you simplify, you're going to get minus 7t square. Then minus 2t plus 10t is plus 8t. Then therefore you have a plus 1 minus 1. So plus 1 minus 1 cancel off exactly, right? Oh, sorry.
Prof, should be minus 2?
Yeah, correct. I forgot the times 2. So therefore you have a minus 1 here. Okay, so if you integrate this, you're just going to get minus 7 over 3 t cubed, then plus 8 over 2, which is 4 t squared, then minus t. Then you sub in the limits 1 to 3. Okay, so if I didn't make any mistake, you should get minus 92 over 3. Any questions on this line integral? Okay, looks good. So therefore, that will be question 8. Question 9. Okay, question 9 also line integrals, but because this one already, they parameterize the path for you already. So you can see there's a r of t, the first path, and the s of t, which is the second path. Then you're supposed to evaluate the line integrals of f over each of the two paths. So this one like mechanical lah. You don't even need to parameterize the path yourself. Okay, so this one just find r prime, then dot product with f, then perform the line integral, and then to repeat the same thing for s of t. Okay, so certainly A I won't do lah. This one you DIY. But B, maybe I will explain. Because they ask, what are the Cartesian equations and directions of path R and S? Hence explain the values obtained in A. Now, the values obtained in A, interestingly, they are negative of each other. Okay, path R, you get half. Path S, you get minus half. So what's the deal here? I mean, is there like a relationship between path R and path S, or it is just purely coincidence? It could be coincidence, could be coincidence. Okay, but let's try to analyze this. So you see, path R is t square, ma. So I mean, this one very easy to evaluate the path. R of t is t squared. That means x equals to t, y equals to t squared, what? Correct or not? So therefore, let me write down. So for path R equals to xy equals to t squared. So this obviously means that y equals to t squared, right? Y equals to t squared, but it's equivalent to x squared, what? So y equals to x squared. So I draw, okay? Y equals to x squared. Then y equals to x squared where t goes from 0 to 1. So x must go from 0 to 1. So therefore this x equals to 0 and this x equals to 1. Path must be like that, because x go from 0 to 1. You see, t go from 0 to 1 here. Okay? So therefore this must be path parameterized by r. Okay? So in the pink color curve. Then let's look at maybe the blue color curve, which is S of t. So S, right, is also xy. But x in this case is 1 minus 2t. Then y in this case is 4t squared minus 4t plus 1. Okay? So that means I can observe that, right, y is equivalent to this 4t squared minus 4t plus 1. Okay, but if you factorize this, you are going to get 1 minus 2t squared. Can you see what? Because 2t, okay, minus 2t squared, you get 4t squared. Then 1 square, you get this plus 1 here, right? Then minus 2t, you get a minus 4t in the center. Can you see, right? So it's actually 1 minus 2t squared, which is still x squared, because x is 1 minus 2t, right? So it is still y equals to x squared. So if I draw the y equals to x squared curve, it's going to be the same curve. It's going to be the same curve. Okay, but, okay, wait, hold on. Okay, move it back. Okay, it's going to be the same curve, y equals to x squared. But if you look at the t values, the t now go from 0 to half, right? The t value, the parameter t value go from 0 to half. What is at t equals to 0? At t equals to 0, your x is actually 1, okay? Wait, let me see. Okay, this one. At t equals to 0, x equals to 1 minus 2 times 0 is 1. Okay? Of course, you can check the y. The y is 1. So y is also 1. Wait, let me see. Y equals to 1. Then at t equals to half. Okay, wait. At t equals to half, you have x equals to 1 minus 1, which is 0. Okay? And can tell you y is also equivalent to 0. You can check. Okay, if you sub in. So which means the blue curve, even though it's y equals to x squared, it's the same curve, but it's the reverse direction. This is going to go reverse. Okay, because it goes from 1, 1, right? This is going from 1, 1 to 0, 0. Okay, but then the pink curve is also y equals to x squared. It's the same path, but it goes the other direction. So it's the same path, but direction reversed. Okay, and obviously that is going to agree with part A, right? Whereby the line integrals are just negative of each other. Okay, so we can write an explanation for this. So for part B, okay, so you can see since R of t and S of t has or have the same curve but in opposite directions, their line integrals are negative of each other. Is that right? Okay, because one is that you integrate from 0 to 1. Then the other one is integrate from 1 to 0. Okay, so obviously integrate 0 to 1 is the negative, right, of integration of 1 to 0. Okay, so obviously there's a negative sign. Any questions on the idea here, on the concept here? So therefore, if you reverse the direction of the path, right, you just have a negative 1 multiplied to the same path before you reverse. Can I? Let me see if there's a chat. Question 6, why no need plus E? Oh, okay. So this one I answered already, right? It can be embedded inside the functions themselves. Right, so this will be for this particular question. So let me move on. Okay, so question 10 I probably will need to do, right? I probably need to do. So you have a radial vector field f equals to xyz, right? You're supposed to show that its line integral over any path is, supposed to show that the line integral over any path on a sphere is always 0. Then sketch a graph and explain why. Okay, this one not so obvious if you try to do. Okay, so the thing is this. Now, because you have a radial vector field, right? Okay, let's say you don't know that this field is radial or what lah. Okay, what we can do, right, is we simply just do our parameterization, and then after that we just try to perform the line integral, and we are supposed to get 0. Okay, it's always 0 ma. So what happens is this okay, so what is the path on a sphere? Okay, because this is the sphere, right? This is the sphere. So what will be the path on the sphere? Okay, let me draw a representation first, then you know better what I'm trying to say. So this is your coordinate, 3 dimensions. Then let's say you have a part of a sphere. Okay, so I'm going to draw like maybe something that looks like that. Okay, so you can see that this is like a section of a sphere. Okay, hold on. Give it some thickness. Yeah, looks nice. Can see Okay, right? So what's the rho? The rho is the 3-dimensional radius ma. So it's like this is rho. Okay, the 3-dimensional radius to the spherical surface lah. Okay, to the spherical surface of the sphere. Okay, so you have a path. So the path on the sphere can be any path lah. Okay, doesn't matter. So therefore, maybe I say that, oh, the path, let's say, look like that. Okay, so this is like path C, for example, okay, that is on the sphere. Okay, so how would you parameterize this path? How would you parameterize this path? Now, obviously, to parameterize the path, you need the R of t, correct or not? So you have a R of t, which is the x of t, y of t, x of t, y of t, z of t. Okay, so this R of t must be pointing to the path. Must be pointing to the path. Okay, hold on. Let me move the path a little bit. Okay, let me just move this radius a little bit away. Then let me just draw an arrow that is pointing to the path C. Okay, so this is your R of t. Okay, but in 3 dimensions, your R of t must be equivalent to x of t, y of t, z of t. Okay, so of course, what happens is that, right, we need to parameterize, we need to compute the velocity vector from this parameterized path. So therefore, we differentiate. So obviously, we just get r prime of t, and that is going to give us x prime of t, right? Y prime of t, z prime of t. Okay, so in this process, I didn't say that, I didn't so-called embed the condition that the parameterized path r of t is on the sphere. Okay, because this is very general, right? I didn't say that, hey, this x of t, y of t, z of t must be such that the path is on the sphere. Okay, I didn't embed that condition yet. Okay, but how do we embed this condition? Okay, first of all, you notice that if I were to find the path integral, right? So integrate, okay, over some curve C, then you have f of r of t dot product with r prime dot product with r prime of t dt. Okay, so this is over path C lah. Then you can observe that this is going to be what? Now, when you parameterize, your f is xyz ma, but your xyz is x of t, y of t, z of t, right? So it means that this f must be x of t, y of t, z of t as well. Hold on, I use a different color so that you can see this more clearly. This is your vector field. Okay, this is your vector field. Underline in green, okay. Then you dot r prime, but you found r prime already, which is here. So you are taking the dot product here and integrating with respect to t. Hold on, I forgot my integration sign. Okay, so if you take this dot product, what do you get? You get x dot x prime. Okay, so let me just omit the of t, too many things to write, right? So x dot x prime, so it's x times x prime plus y times y prime plus z times z prime. Is that right? Okay, so therefore this is an integration. So you take the dot product and then you're supposed to integrate over the curve C with respect to t. Okay, right? So now, right, you look at this expression. Okay, so far everything is general. I didn't say that the path has to be on the sphere. Okay, so up to this stage, everything is general. So now, right, I'm going to look at on the sphere already. Now this is on the sphere. Okay, on the sphere. So our equation is x squared plus y squared plus z squared equals to rho squared. Okay. But after you parameterize, right, everything must be function of t. Okay, so let me write it more clearly. So this must be x of t whole thing square plus y of t whole thing square, then plus z of t whole thing square. Okay, equals to rho. So maybe I should say on the path on the sphere. This one more accurate lah. On the path on the sphere. Okay, we have this equation, right? And notice that now we parameterize already because we have to be on the path that is r of t. So everything is x of t, y of t, z of t. Okay, so x, y, z become parameterized as a function of parameter t. So from here, right, what we can do is you look at this expression and you look at this expression, actually they are kind of related. Okay, what we do is that we just differentiate with respect to t. So d dt. And you notice that you're going to get 2x times x prime. Correct or not? Because you have to differentiate with respect to x first, chain rule. Okay, so bring down the 2. So you get 2x. But because you're differentiating not with respect to x, you're differentiating with respect to t. So you must apply the chain rule. So you times x prime. Okay, so then same thing goes with y. So it becomes 2y times y prime. Then plus 2z times z prime. Then you differentiate rho, which is the radius, you get 0. I mean, it's a constant. Agree? Okay. So you
Wait,
notice that
Prof.
actually this, yes?
Shouldn't be rho square.
Sorry?
Shouldn't it be
Sorry, it's rho square. Thanks. Okay. So this rho square is a constant. You differentiate, get 0. So now you look at this expression, right? Actually, divide by 2 throughout, you're going to get this expression. So we just divide by 2. So you get x, okay, or maybe let me just delete or cancel the 2. So divide by 2, correct or not? So you get this x prime plus y prime plus z prime equals to 0. So that means this integrand is 0. So from here, you're going to see that you're integrating 0 over any path C. So you integrate over any path C, 0 dt. Okay? So since over any path C will give you a definite integral, this guy will be a 0. Okay? So which is shown. Is that all right? Okay? So therefore, let's recap a little bit. So you can see that we parameterize the path, okay? But we didn't assume any conditions that is on this path, okay? So it's just a path in 3 dimensions, right? So which can be parameterized by x of t, y of t, z of t, okay? The x, y, z respective coordinates. Then after that, you differentiate to get the velocity, okay? Still no assumption. Then after that, you perform the line integral, okay? So line integral, we get to this point. Okay, so this is a very general expression, right? For any path or any field in 3 dimensions, you will always get to this expression. Okay, so then we need to account for the fact that the path has to be on the sphere. So therefore, we make use of the spherical equation. Okay, but because the path must be on the sphere, right? So all the x, y, z becomes x of t, y of t, z of t. Okay, because it has been parameterized already, right, by t. So then we differentiate and we realize that we get this expression, which is the integrand being always 0. Okay, so since a line integral over any path c, right, will be a definite integral because you always have a start point and an end point. Okay, so therefore this is a definite integral and therefore integration of 0 will always give you 0. Okay, so notice that we just made the condition that the path must be on the sphere. We didn't specify any particular path. Okay, so this goes to show that, right, the line integral must be 0 for all paths that is on the sphere. Is that all right? Okay, so this is only true if your F here is a radial vector field. Okay, because if it's not a radial vector field, then this will not be XYZ here already. Okay, so it is a radial vector field. So why is it that it is always 0? Okay, so we found that it is always 0 mathematically, but why is it that it is always 0? There's a reason. Okay, and the reason is if you were to draw the radial vector field on the path, then we realize something very interesting. Okay, so let's say, for example, at this point, because the field is radial, correct not? So it must be, for example, pointing in this direction. Then let's say at this point, so radially outwards, so it must be maybe pointing in this direction. Okay, so of course I can draw more points, but I think 2 points is enough. Okay, so what happens is that your path is going to be on the sphere, but the field is radial. So that means you are always going to get perpendicularity between the field and the path. So your field F is always going to be perpendicular to the path. Okay, so maybe I draw one more. So let's say at this point. So this is your field F. And it's always going to be perpendicular to the path. Okay, so therefore, since the vector is always perpendicular to all points on the path C, then it goes to show that the line integral of this F at the path C, right, must always be 0 because the dot product will always be 0. Is that all right? Okay, so this is the reason why you get always a 0 for the line integral. Okay, so maybe I can explain right here, right? Path C at all points. Okay, so F dot dr is always 0. Is that okay?
Wait, Prof.
Yes.
When you integrate 0, why is it still 0?
Because this is a definite integral. Because this, when you integrate over any path C, right, a path C would have a start point and an end point. So that means you are integrating from like t start to t end. Maybe write t start to t end. So like 1 to 2, 0 to 3, whatever. Correct? So
Mm-hmm.
that means you are integrating a definite integral, 0 dt. Then this guy will be always 0, what? Isn't that correct? This is like finding the area under the line 0 that is on the x-axis. It's not indefinite. If it's indefinite integral, then you have a c. Correct or not? You have a constant. Integrate 0, you get constant. If it's indefinite integral, that means you don't have limits. But when you have limits, then you are finding area under curve already. Correct or not? Your 0 is this line. Is there any area under this line? No. No area what? So it has to be 0 area. Okay, good. So I think this is a more challenging question. Question 10. Okay, so this is done. Okay, verifies Green's theorem. I'm not going to do 11 and 12 because I want to do 13, which is your partial question, and that also has Green's theorem. So maybe I do question 13 to demonstrate the concept of Green's theorem. Can ah? Okay. Yeah, so question 13 will be your past year 2024 paper question. Okay. So part A, compute directly the work done by f of xy along path C1. Okay, and anyway, the answers are uploaded already. So maybe I use my answer here. Lesser things to write. Okay, so this one 20 marks. So for A, we are supposed to compute directly the work done along C1. So you can see C1 here, right, is x squared minus 1. Right, x squared minus 1. Then the field is this y 4x squared. So what you do? 7 marks, as usual, parameterization. Okay, so you see, because your path is y equals to x squared minus 1, right? C1, let me write here. So C1, y equals to x squared minus 1. So when you parameterize, right, if you let your x be t, let x be t, that means your y must be t squared. So this must be your y. Okay, so your x is just t, then your y is x squared minus 1, which will be t squared minus 1. Okay, so that's it. So you have parameterized your C1 already. Then next, you notice that actually there's no need to do like separate steps, okay, for your f and r prime, right? If you want, right, you can just do everything in one step, okay, after you parameterize the path. And this is being demonstrated here. So what's f? F is y 4x squared. So the field f equals to y 4x squared. Okay? So because your x is t, so 4x squared is just 4t. Then the y is t squared minus 1. So therefore that's it, right? You sub your y inside. So hold on, let me just change color. So if you let your x be equivalent to t, then your x here, right, it is going to just be 4x squared, which is 4t squared. Okay? So let me underline. This guy is just this guy. Then the y is just y here. And this has to be t squared minus 1. Okay? Because it has to be on the path. Right? We are calculating the vector field that is actually on the path given, C1. So then r prime, just differentiate. So differentiate t respect to t, get 1. Differentiate t squared minus 1 respect to t, get 2t. Then you perform the dot product, and you get this. Okay? Then after integrate, sub in limits. You can see that. Wait, let me see. I want to talk about the limits. Okay, so you can see the limits are 1 to 0. Why is it 1 to 0? Because you have to look at path C1, what? You see? C1 is going from x equals to 1 to x equals to 0 to follow the arrow direction. Can Okay? So that means the start point here is t equals to 1. So t equals to 1 at start point. Okay? But then why is it t equals to 1? Because t is x what? Just now we let x be t t equals to x equals to 1 at start point. Then here, right, is your end point. This one, end point. So t equals to x equals to 0. You see, this x equals to 0, what? So therefore, at end, okay? So it must be 1 to 0. Okay, hold on. Change different color. Okay. So therefore, your limits must be from 1 to 0. Okay, t start to tn. Any objections? Okay, yeah. So then the rest pretty mechanical You sub in, perform dot product, then after that integrate, sub in limits, you get minus 4 over 3. Okay, so this one 7 marks, right? Okay, next, let's look at question B. So question B, it says, using Green's theorem, you're supposed to evaluate the work done by F along the combined path C2 plus C3. Okay, it means using Green's theorem, right, you have to find the line integral from this point. Okay, let me draw. From this point, go past C3, and then after that, go past C2. Okay, so this one use Green's theorem. So how? But then Green's theorem require your path to be closed, what? Correct or not? Okay, cannot be open path, but this one is open, right? It doesn't close back, right, to the start point. So what do? It's okay. You close first. Then you minus off the path integral along C1, what? Can what? Correct or not? Because if you take the path integral C3 plus C2 plus C1, and then use the Green's theorem to evaluate the path integral over this closed path. Okay, there is C3 plus C2 plus C1. Then after that, you minus off the path integral along C1. Then that is effectively giving you the path integral over C3 and C2. Okay, over C3 plus C2. Can? Okay, so that is the idea on using Green's theorem here. So therefore, this is what I mentioned here. Okay, so since C1, C2, and C3 form a closed path, the Green's theorem can be used to find the line integral as, so you see, find the closed path first. Okay, C1 plus C2 plus C3, and that is using the Green's theorem. Okay, so Green's theorem basically just take the so-called cross product dot K lah. So actually this part, actually is here. Okay, so you don't need to write this, right? You can straight away write this. Okay, so this part is actually giving you, del F2 del X minus del F1 del Y. Okay, so this is the expression that we derive in the lecture notes. So you can see, because your F2 is what? 4x squared, right? F2 is 4x squared. So you differentiate 4x squared with respect to x. All right, can you see here? Then you differentiate y with respect to y. Okay, so you're going to get 8x minus 1. Then let's talk about the domain D. Okay, so the domain D, right? This is a double integral over the domain D. Okay, so what is the domain D that is closed by the paths C1 plus C2 by C1 plus C2 plus C3? It's going to be this triangular looking region. Okay, so this is your domain D. So become like topic 7. Okay, or multiple integrals. This is your domain D. Is that all right? Okay. So therefore, maybe I can choose to integrate with respect to y first, followed by x. Okay. So if I look at the y element, right? Y element is like that. That means the vertical element in the y direction. Okay. So that means I must integrate from y equals to minus 1. Can see this lower bound, right? Is y equals to minus 1 to the upper bound. But upper bound is just y equals to x squared minus 1. So this upper bound. You see, so that means my lower limit for the integral with respect to y must be minus 1, and then upper limit must be x squared minus 1. So this is why I have written here. Is that okay? You see? Okay, minus 1 to x squared minus 1. And because I use vertical element, right? Because I integrate with respect to y first. No problem, right? Then what about x? X must be 0 to 1. Okay, because your region D, you can see x go from 0 to x equals to 1. Can, okay? So therefore, you have this integral, and then you just integrate accordingly. Sub in the limits, you can get 5 over 3. Okay, but that's not the end of the answer yet, right? Because this is the line integrals over C1 plus C2 plus C3. Okay, so then you have to minus off the line integral from C1, which already has been found in part A. Okay, so you just take 5 over 3 minus 4 over 3. So therefore, you are going to get a net line integral over only C2 plus C3. Okay, can you see this part here? Right, so 5 over 3 minus become plus 4 over 3. So you get a total line integral over C2 and C3 of 3. Questions? So this is how you can use the Green's theorem to find the line integral along an open path. Okay, so basically just close the path, then minus the part whereby you added to close the path. Questions?
Prof, for the integral for the y coordinates, why is it x squared minus plus 1 and 2?
Why is it x squared minus 1?
Yeah, why is it from x squared minus 1 to minus 1?
No, it's from minus 1 to x squared minus 1.
Sorry, yeah, wrong side, yeah.
This is my domain D. Okay, the whole like triangle, almost triangle shape lah. So this is -1, right? So the lower limit, because you integrate with respect to y first. So that means the lower limit must be y equals to -1. Correct or not? You are using vertical element. Then this upper limit must be what? Is your element is going to be y equals to -1 to y equals to 0, you know. Then this is your element. So if this is your element and you sum from x equals to 0 to x equals to 1, you are going to get this rectangle. You understand?
Okay.
So therefore the upper bound must be bounded by this curve, x squared minus 1.
Okay.
Because then what is going to happen is that when x equals to 0, it's going to be a very short element. Then it's going to add up to the next element, which is lot taller, getting taller, getting taller, getting taller, until the last element, which is the tallest. Understand?
Okay.
From x equals to 0 to x equals to 1, then you can get the whole domain D shaded in blue here. Can I?
Can.
Okay?
All right. Thank you.
Sure. Okay, hold on. Let me also address the x part. Okay, so this is x equals to 0 to x equals to 1. So what this really means is that you're summing up from this line. Okay, because you want to sum up all the vertical slices, the slice of bread lah, right? Sum up all the vertical slices of bread so that you can get this whole loaf. Okay, that looks like a weird shape. Okay?
Can.
Yep. So I have completed tutorial 8 as well as the past year line integral problem. Any questions with the solution? Or you want to ask, anyone wants to ask any like concept questions, like any part that is not clear? Hold on, let me get the thing out. Anyone?
Prof.
Okay, so today for the past year papers, for the past year paper questions, right? At least I've gone through questions 3 and 4. So question 5, you just don't not to worry about it for the exam. Okay, but certainly I encourage you to go through the question just for additional practice after you have viewed the recording that I'll be uploading after your exams. Okay, so that one chill a bit first, right? Don't worry about the surface integrals. Later on, you can have your time to go through, okay, the recordings. Okay. So then
Prof.
I think questions 1 and 2, I'll leave you to go through the solutions yourself. Okay, certainly if you have any problems with understanding the solutions uploaded in Excite, you can always attend the consultation session stipulated to be on Friday. Okay, so on Friday, I already given you the venue already. Okay, if you have any clarifications to make, you can just find me there. Okay.
Prof, so
Yes.
for Friday, is there like a morning tutorial also? Because we normally have a morning and after.
Don't have. Because the morning one, right? Why I didn't put morning is because I found that the morning students you still have this because every time 8 to 10, is it? 8 to 10 or 8:30 to 10, you have something on, right? Then after that, the second group of tutorial students, they will attend the 10 to 12 session. So some students cannot attend the morning session, right? Is that correct?
Yeah.
Yeah, so therefore I put the consultation on the afternoon so that everybody anyone who wants to attend can attend. Isn't that better?
Prof, can you go through question 3 again? I think one of us need to don't understand.
Question 3.
Yeah.
Okay, so question 3. Oh, question 3 is on the triple integral thing, is it? Which part don't
Ye-
understand?
I think the entire question.
The entire question.
Yeah, because the tutorial concept.
Oh, okay, so solid region E here is given by the inequalities here, right? Okay, so then you must observe that the Z is bounded at the lower limit by the root of x squared plus y squared. Okay, so we always try to draw the so-called bounds lah. So once you draw the bounds, then you will be able to visualize the solid. Okay, so without looking at the solution, right? You can see this one is Z so you must draw Z. And then because this is R, so of course you can draw like with respect to R lah. Okay, so this is like root x squared plus y squared, which is really R. Okay, because it's R squared equals to x squared plus y squared. Okay, in the polar representation. So Z equals to R must be like a 45-degree line lah, correct not? But R is in all directions, so therefore this direction is also R So therefore Z equals to R will also appear to be this shape. Okay, so you can see that this is the lower bound. Then the upper bound must be Z equals to 1. This is the upper bound. So Z equals to 1. Z equals to 1 is like maybe this is 1. This is 1. And then you just have a upper bound. Can So therefore, this is showing you a cone. Okay? Because this is just a slice of the cone, a vertical slice of the cone. Okay? If you look at the cone in 3D, this one 3D, then you see the fella looking something like that. Is that right? Okay, where you have a top flat portion that is bounded at Z equals to 1. Can Okay, then this part is trying to tell you that, right, this x squared plus y squared less than and equals to 1 is trying to tell you that actually if you look at the xy plane, then you are going to see a disk, okay? You're going to see a disk because it's a unit disk, right? Then obviously this is the so-called top view of the cone. If you look at you look at this cone from the top, right? You just see a circle, right? You just see a disk. So therefore the disk is the unit disk. And therefore, if you project onto the xy plane, you see the unit disk. Okay, and then if you project onto the zx plane and the zy plane, you are going to see the same triangle. Okay, which is this guy that I drawn here. Okay, because any direction r, if you convert r to x, that means you look along the along the zx plane, is going to be looking the same exact profile, right, as the ZR plane. So therefore, this goes on. This goes to be true to be ZY plane as well, to be on the ZY plane as well. Okay, so the projections are as such. Then after that, the volume. Once you understand this, okay, how the shape of the volume looks like, then you can actually write down the integral more confidently. Okay? So the volume of the heat shield can be evaluated by this triple integral, right? So we can integrate with respect to R first. So you must go from Z equals, you can integrate with respect to Z first. So you can integrate in the Z direction from Z equals to R to Z equals to 1. Why? Because this is the part where the material is what? Correct? You want to get the volume. You have to sum up, right? You have to sum up in the region where the volume is. So what is the lower bound of Z? Z equals to R, as we have evaluated earlier on. So Z equals to R here. Okay? Then Z equals to 1 at the upper bound. But this is in Cartesian. So you cannot write R. But what's R? R is just root of x squared plus y squared. So for Cartesian, you have to put everything, right, in terms of x, y, z. Okay? That's in Cartesian. So therefore, we have this first inner integral with respect to z, and you must put in the limits for the bounds of the cone. Is that all right? You must understand this concept first. Okay, that means whatever direction you integrate with respect to, there must be material there. There must be the solid there. If there's no solid there, that means you're not finding the volume of the solid. Is that all right? Okay. Yeah, so therefore this is integration with respect to z. Okay, bounded by the profiles that we have discussed. Then what about dx dy or dy dx? Now, I can integrate with respect to y first. If I integrate with respect to y first, then you can see that. So it boils down, it returns to the example of the Green's theorem that I went through with you earlier. okay? Because you're integrating now over an area region, like region D, for example, okay? So actually the dy dx integral is over the 2D region D, okay? And because it's dy dx, right? So it must be on the xy plane, you see? So on the xy plane, right, you can see that if I integrate with respect to y first, right, y is usually the vertical coordinate. So I just let it remain as that. And therefore, you're integrating from the lower bound in y. The lower bound in y is minus root 1 minus x squared. Why? Because the circle, the unit circle, is x squared plus y squared equals to 1. So you just isolate the y, okay? Isolate the y. Then you're going to have a plus minus root 1 minus x squared. Okay, so the lower bound is obviously the one with the negative. Okay, because y has to be negative on the lower bound, right? Because below the below the x-axis here, and therefore minus minus root 1 minus x squared to the top bound, which is root 1 minus x squared. So therefore this will be the bounds for y. Okay, and then what about the bounds for x? Then the bounds for x must be minus 1 to 1. Why? Because you want to take the first element at minus 1, sum to the next element, then continue to sum to the next element, and so on what? So you say you're adding up slices. Is that right? So you just keep on summing until the last slice. Questions on part B? Is that okay? Okay, finally part C, actually the same thing. Okay, part C is that instead of finding volume, you're supposed to find mass. So mass, you must integrate density over the whole volume. Okay, integration of density over the entire volume will give you the total mass. So what's the density function? It's the given function here, 1 over 1 plus Rz whole thing square. Okay, then what's dv? Now dv in cylindrical coordinates, right? It's not dx, dy, dz. You cannot use dx, dy, dz, okay? Because that one is for Cartesian. In cylindrical, we have discussed that the dv will just be dz r d theta, dz r dr d theta. Okay, it doesn't matter which order you put. You can integrate with respect to r first if you like, followed by dz and d theta. Okay, it doesn't matter. Okay, but if you look at the expression here, right, because this expression contains r and z, density function is a function of r and z. So it implies that you have to leave theta to the last, okay? Because you have to integrate with respect to the variables that are present in the function first, okay? So theta you must leave to the last. Whether you want to integrate with respect to r first or z first, this one depends on you, okay? Which one is more convenient, right, as you evaluate. So you can see here that I've decided to integrate with respect to z first, okay? It's totally fine. So during this integration, as I mentioned, we can use the substitution, okay? Or you can use reverse chain rule if you can see the relationship more directly, okay? So either way works. So now, let's talk about the limits. So the limits are, once again, r to 1, okay? Because now you see, the thing here is, right, the volumetric region don't change. This volumetric region in Cartesian is the same exact volumetric region as in cylindrical. It's just that you are integrating in different coordinate systems. Okay, but the volume region is the same. The solid region is exactly the same. So you can see z equals to r to z equals to 1 remains. No change to that. Okay, but if you do the integration in cylindrical coordinates, then you'll notice that the dy dx now convert to r dr d theta, right? So that means the second integral must be with respect to r. So because it is with respect to r, the unit disk must be going from r equals to 0 to r equals to 1. Okay? Right? It's the unit disk. So therefore, r equals to 0 to r equals to 1 for the unit disk. Okay, so if I draw the unit disk here, right, you have to go from r equals to 0. Hold on. So this is r equals to 0 all the way to r equals to 1. Okay, so therefore you have your limits for r. Okay, so this will be your limits for r. Can right? Then for theta, it's pretty obvious lah, because it's a whole disk, it's not a quarter of this or half a disk and whatnot, right? So it's a whole disk. So you must go from 0 to 2 pi for the entire disk, okay? So this is theta equals to 0. So you have to spin one complete round around the disk, okay, to theta equals to 2 pi, okay? So you can see that you get the whole disk. Is that all right? Okay, then the rest is integration. So I think I wouldn't talk too much about that. Okay, it's pretty mechanical. It's just that this part, maybe I need to check. Okay, this expression could be like swapped. I need to swap lah. So I'll need just check before I upload the writings. Questions? Any part not clear? Which part is not understandable? Anyone?
Should be fine.
Good, good. Okay. Do you have any other questions?
Prof, is there any more like where to focus on? It's just on topic 7 and 8, right?
Yes. If you look at the past year paper, I would say mainly, or rather like 70% of the marks is on topics 7, 8, and 9 lah. That one is for last year. So this year, it will be mostly on topics 7 and 8. Yeah, because you don't have topic 9, so therefore you are going to get more questions on topics 7 and 8. Okay, because topics 5 and 6 actually is already embedded in the questions for topic 7 and 8. You just look at this integral. You look at this integration. You use substitution, right? You may need to use substitution, right? So therefore, this is already covering topic 5 already, what? Or rather topic 6, okay? So the integration already covered already. And like the, what do you call that? Techniques of integration, okay? So already covered already. More or less lah. So therefore, you should focus on topics 7 and 8, okay? And topic 8 actually requires topic 7 extensively, because topic 7 is your multiple integration, right? Okay. So therefore, for multiple integration, you can see it is also embedded in topic 8. Okay, because topic 8, you can see here. When you use the Green's theorem, isn't this multiple integration, isn't this part integration over a region R or region D? You realize that, right? So therefore, topic 8 is requiring topic 7. Okay?
So it's kind of like more on 7 than 8.
Okay, topic 8 is more for line integrals, and line integrals, you need to know like how to take the dot product, how to parameterize the path. But effectively, eventually after you suck in everything, right, actually it becomes topic 7, because you will get either a double integral or a single integral, right? So eventually it's just like single integration, single variable integration, or you might need to also use multiple integration. Okay, but of course, to get to this point, you need to know how to parameterize the path, right? You need to know how to parameterize the path, how to compute the dot product. So then that will be on topic 7. That's why I say topic 7 and 8 will be the most important topics. Okay.
Prof, which topic is question 9? Which question is topic 9 in this past year paper?
Topic 9 will be question 5.
Okay.
So topic 5 is actually, topic 9 is actually on surface integrals. Okay, so surface integrals, I just briefly introduce, right, 10 seconds. You can integrate a vector along a path, correct or not? Along a path. But you can also integrate a vector over a surface. You can integrate a vector over a surface, okay? And there's a purpose for that, right? One of which, right, is to find, for example, the total flux that is emanating out or that is crossing the surface, okay? So therefore, in the field of fluid mechanics, right, this is being done to find the total flow rate across a surface, okay? Because for any particular surface, right, where there's, for example, airflow, then if you integrate the airflow velocity vectors, the airflow velocity field over any particular surface that is given, you can find the total flow rate of air across that surface. So that is being used in engineering that is to do with, for example, heating, ventilation systems. Okay, because we have airflow across so-called spaces, and we want to know how the air interacts with the spaces that will in turn affects the temperature, the humidity of the thermal comfort inside that space. Okay, so in fluid mechanics, we use that. Then in your E and M, we also use this. Okay, pertaining to the flux of magnetic and electric fields. You may have heard of the term electric flux, magnetic flux. Okay, so therefore, surface integrals, but it's just taking a step further from the line integral. So if you understand line integrals, I think surface integrals is not that big a deal. Okay, so of course you will have to watch the recording that I'll be putting up after your exams. Okay, not to stress you out before your exams, right? After your exam, then I'll put up the recordings. Okay, so that you focus only until topic 8. Any other questions?
Nope.
Okay, good. So enjoy your revision. And then if you have any problems, you need not wait until Friday, right? You can always email me. Okay, but if you want a more face-to-face consultation, right, to understand better, perhaps, then you will just see me in the classroom that I've announced on Friday.
Prof, tomorrow have lecture, right?
No have lah, why got lecture?
Oh, okay.
Tomorrow what? Tomorrow is what? Tomorrow is Wednesday
I
leh.
said, not tomorrow, on Thursday.
Thursday, no more lecture already what? You already finished everything already.
Oh, okay.
Yeah, so I'll only see you on Friday afternoon for those who wants to attend the consultation.
Okay.
Okay, so yep, that's all for today's lesson. Thank you very much for your
Professor.
bye-bye, everyone.
Professor.
Yes?
You mentioned the question 5 is topic 9, right? Or the whole question 5.
Yeah, the whole question 5 is on topic 9.
Okay. Then the question 1B,
B,
is it tested limits?
not tested. Limits, we didn't cover extensively, so not tested on 1B as well. Not tested on the limits question as well.
So 1B and question 5, is there any more that's not tested?
No, the rest all tested.
All right. Thank you, Prof.
Okay, bye-bye.
Alright, thank you,
Bye.
Prof.
Thank you,
Bye.
Prof.